Hi, Saibji Singh Bangar and Amrit Pal and Lail Patel. We are representing our Advanced Power System project. And name of our project is Designing Frequency Control by Variable Loop Control Method in a Microgrid for an upcoming wind battery project for a remote community in Nan, Labrador. And we are submitting this project to Dr. Ashraf Ali Khan. So before going further, we should know about energy scenario of Newfoundland and Labrador. Newfoundland and Labrador has rich hydropower sources, so most of its energy demands supplies are fulfilled by hydroelectric power. Newfoundland's electricity system consists of interconnected grid that feeds most of its consumer. Newfoundland Labrador has 21 isolated rural communities that depends on diesel generator for their energy demands. So Nan is one of the isolated community in Labrador, which is located northmost of Labrador. It is an off-grid community with the population of 1,210. The community rely very much on diesel generator for power supply, and the total annual energy demand for community is 9,280 megawatt. So diesel is coming directly to this community by ships, and energy demands of community is supplied by three generator gensets. The wind power generator, being non-synchronous generators, does not have inertia response and govern capabilities or to control significant frequency variables. So in this project we have focused on variable droop control method to regulate frequency by controlling active power, and MATLAB modeling is used to simulate the effect of proposed 2.3 megawatt wind battery facility in Nine Labrador, along with the three diesel generators that are currently operating to fulfill the community energy demands.
I am Amit Pal Singh and I am going to present before you the fundamentals of frequency control and the variable droop control method that we are going to use in our project. With the increased renewable energy penetration, we are able to reduce the emissions. However, large amount of solar and wind renewables in the grid, particularly in microgrid, can result in instability. Whenever there is a change in load, the change in active power demand has to be quickly met by the generating source. In the case of conventional diesel generators, this was achieved by having a high inertial system. That is, the fuel is injected quickly into the system by the governor of the generator, and the high inertia of the generator is able to meet the uh, active power demand, and hence we are able to achieve the stability in terms of frequency control. However, renewables do not have such high inertial response. Also, they do not have the governor capabilities to control the fuel input. As a result, by using large amount of renewables in the microgrid, we are going to see a transition from high inertial power system into a low inertial inverter dominated power system. Frequency control basically happens in the form of balance between the active power flow generated by the generator and the active power consumed by the load. Whenever there is an imbalance, there will be a change in the frequency and an imbalance in the frequency. For example, if the load or the consumer is consuming large amount of active power and it is more than the amount of active power generated by the generator, then the frequency will fall down and vice versa. The same is true for the voltage also, where the change in the voltage is decided by the imbalance of the reactive power between the source and the load. As a result, a perfect equilibrium or balance has to be maintained between the demand and supply of active power for regulating the frequency in a system. Uh, for example, if it's a 60 hertz system, as in the case of North America, whenever the equilibrium between the generation and the consumption of active power is achieved, then there will be a stable frequency. There are two methods of frequency control. One is droop control method and the other one is rotor inertial control. Our focus area is droop control in this project. However, there is a limitation in the droop control method because of the line inductance and capacitances and because of the grid frequency imbalances. We often see power oscillations which may be of larger magnitude in the case of droop control. So, in order to solve this problem, we have replaced the droop coefficient by coefficients of active and reactive power in order to regulate the frequency, and these are given as indicated by the formula. So the droop control frequency is given by the rated frequency, and from that a factor is subtracted which is given by the droop control coefficient multiplied by the difference of the actual active power and the rated active power. Similar formula is applicable for the droop control voltage also. This slide basically indicates the basic model that we'll be using in the system modeling. On the left hand side, you can see the DC output of the renewable energy is fed to an inverter, which basically converts the DC into an AC output, which connects to the load or the microgrid. And in between, we have the LC filters. So the task here is to control the firing of the inverters based on the active power flow so as to control the frequency. So the load and voltage and currents are measured by voltage and current transformers for the three phases, and as a result, we are able to convert the ABC values into DQ parameters. This allows us to do the power calculations, and as a result, we are able to know the actual active and reactive power flowing into the loads or the microgrid. Uh, to the adaptive droop control, we also feed the reference frequency and the reference voltage that we want to achieve. And basically, this adaptive control is simply mimicking the aspect or the functionality which the synchronous generator used to perform. So we feed this into a PI power PI controller, and the task of power PI controller is to remove the difference between the actual P and Qs as compared to the desired P and Qs. The output of the power PI controller is fed into a current PI controller, and the task of current PI controller is also to reduce the difference between the desired current that we have achieved from the right side to the actual current. So based on the current PI output, we generate PWM output pulses which control the firing of the inverters. So in this way, we are able to regulate the active power flow into the microgrid, and based on the load fluctuations, the active flow can be regulated so as to regulate the frequency of the system. In the subsequent slides, my friend Lei will now indicate how these models have been made in the MATLAB, and will discuss the results of the MATLAB simulation.
Hi, my name is Lay, and in upcoming slides, I'll going to explain simulation of frequency control in NAND location. So we have modeled diesel generator of 1.5 megawatt with 2.5 megawatt of wind farm, which is proposed in NAND location. It's coupled with a transformer, which is 400 volts to 600 volts on secondary side. So in upcoming slide, I'll present the simulation and simulation results. So as we have proposed frequency control by droop control method, so it is very important to set the frequency droop set points and the voltage droop set points as well. So as shown in the figure, if active power increases, frequency get decreases, and vice versa. If active power get decreases, frequency increases. So group control maintain frequency in between frequency set points. So in MATLAB simulation, we have set frequency set points at 1% deviation. So frequency can vary from 59.7 hertz to 60.3 hertz. Apart from that, active power also can vary. 10% from its rated output. So in upcoming slide, I'll present the simulation. So this is the MATLAB simulation block diagram which is carried out in MATLAB Simulink. So this block diagram represent existing diesel capacity which is 1.5 megawatt. This is the MATLAB inbuilt diesel generation system, and this is the wind farm of 2.5 megawatt, which this both are connected with the point of common coupling, and there is a load also connected with that. And I have added the variable load with that to check the dynamic condition with increasing load as well. So this is the control diagram, control system for this wind and diesel hybrid system. And these are the measurement that we are carried out: frequency, active power, reactive power, and grid voltage. So in this simulation, we are going to increase load at 1 second, and group control will enable at 3 seconds, and supervisory control enable at 5 seconds. So these are pre-data entered in this control diagram to check the simulation effect on this wind diesel hybrid system. So in block diagram of 2.5 megawatt wind farm, this is a submodel of that wind farm. So there is a two-level converter which is connected with the LC filter, and that is connected with the transformer which is 480 on primary side and 600 volt on secondary side. The gate pulse of two-level converter is given by this control system. So we are converting ABC grid voltage to DQ reference voltage, and from that PI controller we are supplying gate pulse to this two-level converter for controlling the frequency of the grid. So this is the frequency deviation captured during simulation of 8 seconds. So as there is a load increase at 1 second, you can see the frequency deviation, and at 3 second group control is in act now, and at 5 seconds supervisory controller is enabled. So as you can see, the frequency deviation is within the limit of 1% of group set points, and when supervisory control gets on, frequency try to reach 60 Hz at a steady state value. So from this simulation result, it shows the point of common coupling bus voltage. So this is the grid voltage of point of common coupling, which is maintained at 600 volt. Uh, just because of group control and supervisory control when there was an increase in load. So it shows the grid voltage maintained within the set point set earlier. This is the simulation result of active and reactive power of grid. When there was increase in load at 1 second, active power and reactive power both increases, and the active power increases from 1200 volts to 1600 volts. So from the earlier result of frequency and voltage, we can see the frequency stability is within the range, and voltage is also within the range. So to conclude our presentation, NAN is of course very remote location in Labrador, and which is not connected with the Newfoundland grid and Quebec grid as well. And it is not possible to connect with Newfoundland grid or Quebec grid because of high transmission cost. So with this upcoming wind battery project in NAN, there is a high renewable energy penetration in this microgrid. So it will be having issues of frequency regulation and voltage regulation if we have a high penetration of renewable sources. So with this group control inverted microgrid method, it is simulated that the frequency variation and the voltage variation is within the set point, and that can be effective solution to control frequency and to maintain voltage across the grid. Finally, thank you for listening our presentation and have a good day.